All right, so welcome back. Before we get started on our today's lecture, I want to do a quick review on things that we covered so far. All right, so in our chapter 1, we started by talking about terms of thermodynamics. Remember, we'll start talking about closed system versus open system. We'll talk about equilibrium, reversible, non-reversible processes, and also like what exactly is work, how do we calculate the reversible work that's been done for a process. Right? In chapter 1, we have also covered materials like ideal gas law. So looking at ideal gas law, we derived the PV equals to nRT using the two experimental observation, which is the Boyle's law and Charles' law. So remember, these equations of state are experimental state that we derived that describes relationship between pressure, volume, and temperature. And in this process, we have extensive versus intensive properties and so on. Also for ideal gases, one thing to keep in mind is that the internal energy is only dependent on temperature. It's independent from pressure or volume. But when we're looking at all these equations, it's important to keep in mind, like, what are they applicable for, right? So the common mistake people make in this class is just picking a random equation without understanding what that equation is suitable for, and then leading to the wrong result. So for example, in this case, when we write dW equals to negative PdV, so this is only applicable for reversible processes. And remember, when we say a process is reversible, we're saying like, hey, it's a very slow process, and any small changes will lead to the will switch the direction for the system to go back to its original state. So it's a very slow process that's reversible. Like for example, when we're using the first law of thermodynamics, typically in this class we write it either as delta U, the change of internal energy equals to heat plus work, or if we're looking at the infinitesimal changes, we're writing du equals to dq plus dw. All right, so for use of the first law of thermodynamics in these forms, we're assuming the system is closed, at rest, and no external field. Right, so remember the initial form of the first law is delta E equals to Q plus W. Right, so these terms are eliminating the kinetic energy and potential energy in the first law of thermodynamics. Yes.
What was the second term again? Closed?
At rest.
Oh, at rest.
So at rest tells us, okay, there's no kinetic energy, right? So, and then there are things that are just true by definition. Like for example, we manually define enthalpy, right? So enthalpy is a term that we define it to be internal energy plus PV. So there's no like things we use at the end to say like, this is only true for closed system or so on. Enthalpy is just by definition equals to U plus PV. So this is a very nice point for me to just like quickly pause here and try to illustrate like when using equations in this class, it's very important to know what is the setup and what are the appropriate equation to use in this class. All right, and just to highlight some of the differences, there are things that are just generally true. There are equations that's only true for ideal gases, and keep in mind these equations are only true for ideal gases. If we did not specify an ideal gas, do not use these relationships. Yes.
What is internal energy like if we don't make those assumptions?
What do you mean by internal energy? Is the energy, well, the total energy equals to U plus K plus V. Right, so internal energy is just the energy of the system, assuming it is at rest, no external field. We will talk about the nature of internal energy when we talk about the movement of the particles in statistical mechanics. But for now, internal energy is something that's just the property of the system that we care about. it's rooted in the movement of the molecules or atoms in the system, but we will we'll save it until we discuss statistical mechanics. So right now, knowing that internal energy is just everything that's not kinetic and not potential. All right? Okay, so this is a quick review. And for this lecture, we'll keep going as follow-ups on our first law of thermodynamics. So we briefly touched on heat capacities, focusing on specific heat. So today we'll first give heat capacities a more precise and accurate description in the vocabulary of thermodynamics. And then we'll go over the two experiments, the Joule-Thomson experiment. So these experiments are set up so we have a mean to measure how does my internal energy or my enthalpy, H, will change with respect to the change of thermodynamic state. Like for example, it's more straightforward to imagine we can measure the change of internal energy versus temperature. But say if we ask how does the internal energy U change when volume change, right? So those are the things that are not very straightforward to measure, and we have to set up experiments carefully and using partial derivatives or calculus relationships to help us solve for these changes or relationships. So let's get started with the heat capacity. So we used specific heat before, and remember the previous case we were talking about, hey, what is heat, right? So we simplify it to say like heat equals to mass times specific heat times the change of temperature. Now the more precise or the more accurate definition of specific heat is for any infinitesimal processes in a closed system. So this abbreviation PR that you will see under that big letter C. So that's stands for like for any processes we might have. And this heat capacity of that specific process PR is defined as the infinitesimal change of the heat flow. So this is the dq PR over dt. All right, so heat capacity is basically the derivative of your heat transfer over dt. So that's a definition of our heat capacity. In thermodynamics, we have two common heat capacities that we will be using constantly. For example, as we were saying, for any infinitesimal changes in a closed system. So in this case, we can define that infinitesimal change as the process of an isobaric process. So remember, isobaric tells us that's constant pressure. Right, so instead of writing that PR, we're now writing P. That subscription P just tells us, hey, this is the isobaric heat capacity that's measured at constant pressure. Now, if you think about it, our CP, by definition, equals to the infinitesimal change of your heat at constant pressure over dt. And at the end of our last lecture, we went over the discussion of what is the physical meaning of enthalpy. And remember, our conclusion is that for isobaric heat transfer, these are our enthalpy. All right, so in our end of our last lecture, we concluded that dH equals to dQp. Or instead of writing that as a QP, you can also write it as a partial derivative. So we're talking about the partial derivative of enthalpy over temperature at constant pressure. So this constant pressure comes out in that partial derivative. Yes?
Is the dT the change in total temperature?
Changing temperature of the system. All right, so in this class, unless we're otherwise specified, we're always saying, hey, we're focusing on the system. We're focusing on the system only.
enthalpy into that? And I guess follow-up question, how do you take the derivative of PV at constant pressure, I mean, with respect to temperature? Would we need to find like a relationship between volume and temperature? And so how would you do something like that?
So in this case, first of all, these are just say, we're trying to give CP a definition. And then the question becomes, how do we actually measure it? And how do we actually link the heat capacity we measured to something that we care about? Like how does enthalpy change with respect to volume? So in this case, we'll see in the later section in how do we set up an experiment where enthalpy is kept the same. So we have a relationship between, hey, the change of temperature and pressure, and then use that relationship into connecting CP. So thermodynamics basically is a subject that we use these partial derivatives. We use these calculus to make connection between things we can experimentally measure and things we cannot experimentally measure. So the quick answer to your question is, can we substitute the definition into this equation? Well, it depends on if we need to do so. All right, so if there is a need to do that, and we will do that in the shortly after, and we'll see how that applies. And like the isobaric heat capacity, we can also have isochoric heat capacity. And remember, isochoric heat capacity means we're looking at constant volume, or we write it as CV. So in this case, CV then equals to the change of, the infinitesimal change dQV over dt. And what exactly is this dQV? I already give you the answer, but we'll do a very quick derivation. So in the setup here, we're saying it's a closed system, PV work only, and equilibrium, right? So there are several things we can use. And like I'm gonna leave out the at rest and no external field from now, just for this class. Typically, we don't care about kinetic energy and potential energy. So in this case, there are several toolbox we can use. First of all, we have our law of thermodynamics. The first law of thermodynamics, du plus dw. And the other way to put it, we're talking about a constant volume process and reversible PV work only. We know it is reversible because it states that this is for equilibrium, right? So at equilibrium, you only have like infinitesimal changes or very slow changes. So in this case, we have our dW equals to 0 because our dV is 0 for isochoric processes. So dV. All right. So this is how we derive the heat transfer or isochoric heat transfer, QV, equals to the infinitesimal change of internal energy. And then we can rewrite our CV equals to the partial derivative of U over T at constant V. All right, so we will be using these relationships later on, but keep in mind like the assumptions we made to make them true. Or the other way to put it in plain English is what's the physical meaning of heat capacity? So the CP is the rate of change of enthalpy with respect to temperature. CV is the rate of change of internal energy with respect to temperature. And since heat capacity discuss change of these thermodynamic state functions with respect to temperature, it doesn't exist a heat capacity for isothermal processes. So if we don't have any change in temperature, we don't have a heat capacity. Now, before we move on to do a little bit more math, I want to ask you a question. Is our heat capacity, CP and CV, extensive or intensive property? Okay, so think about it. Are they intensive or extensive? Raise your hand if you think CP and CV are extensive property. And raise your hand if you think they're intensive property. So in this question, they are extensive property. And keep in mind why that is the case. We have CP equals to the, well, using CP as an example, CV works the same. CP equals to the change of enthalpy with respect to temperature. Now our enthalpy or my internal energy, these are external properties. All right, so we don't have, we must take that into consideration that since H and U are extensive properties, and taking derivative of T doesn't change the number of moles in that system. Now my CP and CV must be extensive properties. All right. And since they are extensive properties, we have intensive versions of my heat capacity. So if you divide CP with number of moles, you get the molar heat capacity. If you divide these heat capacities by mass, then we have our specific heat capacities. But the heat capacities themselves are extensive properties. All right, see if we have any questions before we do some example problems together. Yes.
So a little confused on how it's extensive because, you know, like when you have more of something, it's going to be more heat. So.
Yeah, that's why it's extensive.
Yeah. Oh, wait.
That's what you were
Okay,
saying,
never
right?
mind, never mind.
Because when you have more of something, you have like more of enthalpy or internal energy. So as a consequence, that change of your enthalpy or internal energy with respect to temperature will also be bigger or proportional to the amount of substance you have. All right, so this is the kind of example question that I hope you can keep thinking about, because we went over all those terminologies of thermodynamics, right? Extensive, intensive, homogeneous, heterogeneous, open, closed, like these are just a little bit jargon-like, but whenever we encounter like a new property, just give it a careful thought and like, what exactly is it? Like, what exactly is the physical meaning behind these symbols on paper? And now we're ready for some example questions. So if you have a copy of the blank note, perfect. If you don't, I have some printed out for you. So we'll do these problems together here. First question, given that a hypothetical equation describing the internal energy of a substance, right? Internal energy equals to some like ANTP squared plus N times BT plus BP third minus PV, etc. It's very long. But nevertheless, can you write out an expression of CP and CV? And if not, explain like why you cannot write out an expression for it. Let me just write out the expression for CP and CV to refresh your memory. So CP equals to partial derivative of H over T at constant P. CV equals to partial derivative of U over T at constant V. So I'm just going to write as you were writing, and then we'll look at it together. How we do? So, well, we solve for CP first. CP is, well, again, we start by using the definition of the terms. We know that CP gives us the partial derivative of enthalpy over temperature at constant pressure. So we write, first of all, an expression of enthalpy using the definition of enthalpy, which equals to ANTP squared plus N times BT plus beta P to the third. Right, so this entire term, we're trying to solve what is the derivative of all of these terms with respect to temperature. Looks complicated with lots of symbols, but it's effectively just a calculus problem. The first part is, well, T disappear, and the second part, we use a very simple calculus tool by setting x equals to BT plus beta P and solve for dx over dt, and then use that to write out an expression. Right, so the CP part is pretty straightforward. Yes? What's that? Oh yeah, it should be squared. Yes, thank you very much. And the CV term, now this one, like, don't jump too fast in solving the derivatives, but give it a careful thought. Because in the expression of our U, we have this term PV. Right, so remember when we have this term PV and at constant volume, this partial derivative of PV over T at constant volume, well, basically, well, we take the volume out, it's a constant. It's a volume times dP over dt at constant volume. Now, this is part of equation of state that describing the relationship between volume, pressure, and temperature. But the question didn't give us an equation of state. So this relationship is not solvable. We are missing information. Yes?
You treated pressure as a constant in the other terms.
Yeah, well, so remember, when we're solving for CP, we're treating pressure as a constant because we're claiming the pressure is a constant when solving for CP. But when we're solving for CV, we can't specify pressure as a constant. We only specify volume as a constant.
So the whole term is just non-derived.
Yeah.
It's not just the PV at the end.
Well, yes and no. So in this case, we're solving, well, that's also true, right? So we're just saying like this, I'm just using this last term as an example to say like this is not solvable because at least one of them is not solvable. Other terms might not also be solvable. But in this case, if you think about this problem, now if I give you one more thing, like say this one is an ideal gas, and then we have enough information to solve for the specific heat. All right, so it just depends on what exactly is the question we're talking about. Or instead of giving you as an ideal gas, I'll give you some other equation of state, say like volume equals to like A plus BT squared. So, or like, and then, well, PV equals to A plus BT squared. All right, so this kind of relationship will allow you to solve this equation further. Yes?
So it's not, I'm just confused why it's not solvable. Is it because you can't isolate the pressure?
No, so in this case, we end up, I'm just using this as an example, right? We end up writing an expression to say like, eventually we have to solve this partial derivative of pressure over temperature at constant volume. Mm-hmm. But reading the problem, I have no idea how my pressure is gonna change with respect to temperature. It's not given.
Okay.
So that's why we cannot further solve it.
Okay, so even if you isolated it to be P equals U minus whatever the rest of the equation, like P on one side.
Well, either you don't know U or you don't know P. But in this case, we're like, don't dive into the math too much. That's my point of view, right? Don't try to dive it in and waste your time. Just think about it. Like in this case, what is the physical meaning of that partial derivative? We're talking about a relationship between pressure and temperature. Now, the problem only gives us an expression of internal energy as pressure, volume, and temperature. So there's no way we can know how does pressure change with respect to temperature. All right, so that's going to save you lots of time when working on exam questions or homework problems. Like, don't dive too deep into like, hey, I need to write an expression of pressure, and then it's like, oh, I still can't solve it because I have an internal energy somewhere, right? So it's just to save you some time by just looking at the equation itself. Yes?
So you're saying if you were to do the differentiation, because you don't know how U works with T, you would get a du over dt, and that's unsolvable?
Well, so in this case, what we're trying to solve is du over dt at constant volume, right? So this is what we're looking for. So we don't know it, otherwise we don't have to solve it. Okay, so that's one example question. The second example question, this one is something, again, let's do it together. We're trying to derive a relationship between these two heat capacities. So the relationship we'll be using, first of all, let's use Cp, that again equals the partial derivative of enthalpy over temperature and constant pressure. Cv equals the partial derivative of internal energy over temperature at constant volume, and the definition of your enthalpy. So for this question, we will do a more like general derivation, saying like only using these relationships to get a general expression on what is the relationship between Cp and Cv. And then we'll look at a special case, like what if for ideal gases, what are we solving here? So in this case, again, what we're trying to solve is the relationship between Cp and Cv, right? So in this case, they have the same dimensionality. We're talking about the same thing. Your enthalpy and internal energy have the same unit, so my Cp and Cv naturally have the same unit. So we can take minus of them and thinking about how to solve for an expression of Cp minus Cv, just using the three equations we have here. So likewise, we'll work on it together. You can start writing yourself, and also like we'll check later on. And I hope people in the back can see my handwriting. Okay, it's big enough. So I'll pause here and then we'll keep doing. So first of all, what we did, we're writing our CP minus CB, right? So naturally, what we're writing is the expression of CP and CB based on their definition. And then in this case, on the right-hand side, we have the internal energy, and as you were saying, whenever we need it, we want to use the definition of enthalpy as like U plus PV to write it out. So we can further simplify this relationship without having a DH around. Now in this case, since we're looking at constant pressure, so then this term in the bracket becomes the partial derivative of U over T at constant P plus pressure times dV over dt at constant P. Again, we can take pressure out because we're talking about constant pressure process, right? And then we have this term, again, it's keeping it around. Now, observing this expression, how can we further simplify it using calculus? So the way to think about this problem is looking at it. On the left-hand side, we have du over dt at constant P. On the right-hand side, we have du over dt at constant V. Now, I'm going to leave this one here for now since it's related to the equation of state. But looking at these two terms, the question we're trying to answer is like, is there a way we can connect these two terms only using calculus and further simplify this relationship? And the way to put it is, let's say we know that internal energy is a function of temperature and volume. You can also say temperature and pressure or volume and pressure because the T, V, and P are somehow interconnected, right? But nevertheless, we know that internal energy is only dependent on either, well, two out of the three. So we're using temperature and volume in this case. We can just simply write the total differential of internal energy. So this is just calculus. We know that for a function that has two dependent, you can write the total differential of that function as partial derivative du over dt at constant V times dt and also du over dV at constant T times dV. All right. And then we want to move this term to the bottom. So we have this term here. This is something we want to connect with du over dt at constant P. So after moving dt to the bottom or divide both ends by dt, we get an expression of du over dt equals to partial derivative of u over t at constant v, and also the partial derivative of u over v at constant t, and dv over dt. Yes?
Why exactly are you dividing by dt?
I just want to move this around, so I got this term out, because this is something we want. I want it out, like without any dt around. That's the whole point. And then, in this case, what we want at the on the other side is du over dt at constant P. All right. So if we manually set it to be, say, hey, this is at constant pressure. Let's assume it is under constant pressure. Then this term, du over dt, we can write it as, well, it's the same as du partial derivative of u over t at constant P, and this doesn't change. U over dt at constant E, and this term, the normal derivative, also add a constant pressure there. So that's how we get an expression of this term as these partial derivatives. And then we can plug it in back to our original equation. So we have Cp minus Cv to be equal to, well, du over dt at constant V plus du over dv at constant T, dv over dt at constant P plus P times dv over dt at constant P minus du over dt at constant V. So these two terms then cancel out. Again, we're trying to find a relationship between Cp and Cv. So these are just my Cv term, and naturally they should be canceled out because we don't want a Cv in the relationship between our Cp minus Cv. And what we end up getting is Cp minus Cv equals to, well, this thing here, we have dV over dt at constant P. So that's the du over dV at constant T plus pressure. And this entire thing times dV over dt at constant pressure. So I'm just going to copy that onto the iPad so we can do the second step together. So why do we care about this relationship? Again, the whole point of thermodynamics is we do experiments to get the relationship between, say, your internal energy with respect to temperature, pressure, volume, etc., etc. But ideally, we want to do as little experiment as possible, right? So we want to use calculus to simplify our life and say, let's find as much relationship as possible so we do not need to do a separate experiment for every thermodynamic relationship that we care about, right? So in this case, after finding out the relationship between Cp and Cv, we have a way to measure things that we, well, typically don't have means to measure, or vice versa. Now, in this relationship, there's one more thing, which is this du over dV at constant T. So that's our internal pressure. I'll leave it to you to think about why this term is called an internal pressure by deriving the unit of this partial derivative du over dV at constant T. But nevertheless, before we do that, let's do one more practice using this relationship here. Again, as we were saying, what we did on the board are the more general derivation on the relationship between your Cp and Cv, right? The only thing we use are the definition of Cp, definition of Cv, the definition of enthalpy, and calculus. That's everything we used. So this equation is a general equation describing the relationship of Cp minus Cv. It doesn't matter whether it's liquid, solid, gas, or whatever it is. However, in this equation, obviously, knowing the equation of state will help us to further simplify the relationship between Cp and Cv. So let's starting by to use our ideal gas law. So these are the two things we will be using. Now, assuming we're looking at ideal gases, can we solve for the difference between your heat capacity, Cp and Cv, using the ideal gas law? So in this process, if we're using ideal gases, what do we know? We know that, first of all, for ideal gases, our internal energy only depends on temperature. So this term, du over dV at constant T, becomes 0. For ideal gases only. Again, now we're just moving on to the assumption that we're focusing on ideal gases. And then for ideal gases, we know that change of your internal energy versus volume at constant T is 0. And at the same time, we have PV equals to an RT. Now, do we have a mean to solve all these partial derivatives? And the answer is yes, we have enough information to solve for CP minus CV for ideal gases, yes.
For that first assumption, I don't remember seeing that.
This one is just saying like for ideal gases, they don't have volume. The ideal gas molecules are just like dots. They don't have volume, they don't interact with each other. So the only thing matters for ideal gases is temperature. So this one is like, so whatever on this side is like given to you. I don't expect you to like remember everything, but it's nice if you start to develop your own equation sheet as we go. Yes.
Is that having to do with like where we assume pressure is almost zero for ideal gases?
What pressure?
The pressure is almost at zero.
Uh-huh.
Is that what that's referring to?
No, so when pressure is almost zero, the gases are behaving more ideally because they have minimal interaction with each other. So that's the kind of assumption people make. Well, we live in a real world, right? So we don't have real ideal gases in our world, but scientists need to have a way to mimic how ideal gas perform. So that's a different assumption in the actual experiments. But now, in this case, since we know these relationships, we can solve for Cp and Cv. So Cp minus Cv thus becomes, well, inside the parenthesis, 0 plus P times dV over dt at constant P. So d over dt at constant P, that's nRT over P at constant P. So this term becomes P times nR over P. And our result is that for ideal gases, the difference between your isobaric heat capacity and isochoric heat capacity is always equal to N times R. Yes.
So the CP minus CV equation up there is generalized for solid, liquid.
This one is generalized because remember when we were deriving it, we only use the definition for CP, CV, and enthalpy, right? There are things like we need, like closed system, you can't have heat transfer, you can't have material transfer, closed system, PV work only, equilibrium, right? So, but those are the only things we make. It doesn't matter what is the nature of our system when deriving this equation.
Okay, but we just used information that we have known from previously to
Yes.
Apply it to ideal gases.
Right, so then using this equation and what we know about ideal gases, we can further solve for a set relationship between CV and CP for ideal gases. So a type of question you could expect, again, we can give you a different equation of state for a hypothetical material, and you want to know how to solve for that relationship. And by the way, back to our discussion on if Cp and Cv are external and internal functions. So now it becomes very obvious, right? So you have the difference between Cp and Cv is nR, or you can write like Cp equals to Cv plus nR. So this nR is obviously an extensive. You have a number of more in there. So your Cp and Cv must be extensive. So back to our discussion there. It is a little bit counterintuitive, I know, because we started learning it using specific heat. And specific heat is Cv divided by mass, and that is intensive. So. Okay, we only have 4 minutes left, so I guess I don't want to keep pushing it. But if you have your blank lecture note, keep it. We will be using it in our next lecture. But do we have any questions before we move on? Yes?
For that portion, can we go over the ideal gas, how you got U is 0?
This one is just given. So for ideal gas, gases, this goes to the nature of the internal energy. And remember, we're not talking about the nature of the internal energy until statistical mechanics. So for now, just like accept the internal energy is only a function of temperature for ideal gases.
Okay, so it's just a given.
Yeah, for now, we have to say this is given because we haven't talked about statistical mechanics yet. Any other questions? All right, so our next lecture, we will talk about the Joule-Thomson experiment. Or more specifically, the Joule experiment and then the Joule-Thomson experiment. So these two are experiments that scientists set up to manually have a relationship where your internal energy is kept constant or your enthalpy is kept constant. And then by doing these experiments, we have a mean to connect the change in internal energy or change in enthalpy with respect to volume or pressure, depending on the system we're interested in. But I hope today we give you a good demonstration in like, hey, thermodynamics is a study for relationships. We're always talking about relationships of different properties that we can measure and something we care about. And I hope that's the take-home message. We do lots of math, but I really don't want you to leave this classroom and say, hey, that's just a math class. So in this case, we do the math so that scientists can do less experiment to get the relationship they want using calculus. So calculus is a tool. The goal is to get relationship between thermodynamic properties. All right, that's all. I'll see you on Friday. Yes, Friday.